Hi, thank you everyone to join this open source conference. I'm Jiewen Yao, Principal Engineer in Intel. Today, we will introduce a virtual firmware for Intel Trust Domain Extension technology. To introduce myself, I'm Jiewen Yao. I've been engaged as a firmware developer for over 15 years and package maintainer in open source UEFI firmware EDK2. I'm architect for the virtual firmware for Intel TDX. TDX introduce architecture elements to help developer hardware-isolated virtual machines called trust domains. Intel TDX is designed to isolate VMs from the virtual memory manager, the hypervisor, and any other non-TD software on the platform to protect the TD from a broad range of softwares. On the left-hand side, the red box shows the legacy VM. This is a traditional VM or hypervisor environment. The hypervisor has the highest privilege. It can access or modify the VM environment. On the right side, the green box shows the TDX Enlightened OS running in a TD. With the help of TDX hardware and a special Intel TDX module, the TD is isolated from VMM and other TDs. Inside of the TD, the memory and the CPU state confidentiality and integrity is provided to keep the sensitive IP or workload data secure from most software-based attack. The TDX uses MKTME for memory encryption. It can also augment some hardware attack, such as offline DRAM analysis or DRAM interface hijack. In a traditional VM and hypervisor environment, we need a virtual firmware to provide services to the guest OS. For example, the EDK2 Open Virtual Machine Firmware, OVMF, provides the UEFI services in the virtual firmware. It is also true for TDX. A TD virtual firmware is needed. We call TDVF. The TDVF owns the first instruction of a TD, which is a reset vector. Similar to the traditional OVMF, the TDVF provides the UEFI services to guest UEFI OS. The TDVF enabled the trust boot capability to build a trust chain from the Intel TDX module to the TD-OS. The current TDVF implementation is based upon EDK2 OVMF. In order to reduce the TCB, we removed the PI phase. The TDVF has a sec phase and a sec core initialize the memory and jump to the DXE core directly. After DXE core boots the BDS phase, it loads the operating system and boot into operating system. Here is a high-level flow of the TDVF. The black color means the flow is similar to OVMF. The orange color means the flow exists in OVMF and it is updated in TDVF. The red color means the flow does not exist in OVMF and it is unique in TDVF. The reset vector in TDVF is different. The traditional OVMF has 16-bit real mode entry point, but the entry point in TDVF is 32-bit protected mode. The VMM can pass a TD parameter, also known as TD hop in RCX or R8 in the CPU init state. The TD hop may contain any information that the VMM wants to pass to a TD dynamically. For example, the guest physical memory location, the MMIO location, etc. After the TDVF switch from protected mode to 16-bit long mode, it passes the TD hop header and gets the size. Because the TD hop is external input, the TDVF measures the entire TD hop to the TD runtime measurement register to support the trusted boot. Once the TDVF gets a memory location from the TD hop, then the TDVF sec initializes the private memory. Then it prepares the PI DXE hop and locates the DXE core and jump to the DXE core. In DXE phase, it does regular DXE initialization. For example, it needs the memory management, the CPU multiprocessor UEFI variable. It enables the UEFI secure boot to verify the third-party code such as OS Loader. It enables the trusted boot to extend the firmware configuration and third-party code into TD runtime measurement register. It prepares the required ACPR table for the guest OS. If SEC does not initialize all memory, the rest memory will be initialized in DXC phase. Because the default memory is TD, and TD is encrypted, it cannot be used as a virtual device for DMA buffer. To support the virtual device access, the TDVF has a special IOMMU driver to switch a private encrypted memory to a shared memory for DMA access. After all DXC drivers are dispatched, the TDVF enters the BDS phase. It enumerates the VirtIO device, starts the console devices, and starts the storage devices. Then it boots to the OS loader and boot to the OS, similar to a normal OVMF. The TDVF binary is similar to an OVMF binary. It is constructed with UEFI PI firmware volume. We put all UEFI drivers into a boot firmware volume, known as BFV, and the UEFI variable configuration into a configuration firmware volume, which is known as CFV. Inside of the BFV, there's a TD descriptor metadata. The offset is at 4 GB minus 20H. The TDVF descriptor includes the binary information, such as where's the BFV, where's the CFV, where's the temporary memory, and where's the TD hop. Those information will be passed by the VMM when the VMM creates a TD hop and load the corresponding data to the TD. The CFV holds the provisioned UEFI variable, for example, the PK, KEK, DB, DBX, which will be used for a UEFI secure boot. A TD starts from the protected mode reset vector. The address is same as 16-bit real mode entry point, FFFFFF0. The initial state of the general purpose register has some special meanings. For example, the IBX holds the guest physical address width information, also GPAW. The GPAW is either a 48-bit or 52-bit. If GPAW is 48-bit, then the guest uses four-level paging. If the GPAW is 52-bit, then the guest should use 5-level paging. The RCX or 8 holds a pointer to the TD hub. The TD hub contains the TD information such as memory information and MMIO information. The RSI holds the virtual CPU index from 0 to n-1, where the n means the total vCPU number. The multiple CPU supports in a TDX is totally different with a traditional mode. In traditional mode, only BSP is launched to a reset vector, while the APs are in a wait for CP state. The OVMF BSP need to send init CP sequence to wake up APs. However, in TDX, all CPUs jump to the reset vector at the same time by the Intel TDX module. The Intel TDX module can guarantee the virtual CPU index is from 0 to n-1, and n means the total vCPU count. The TDVF can treat vCPU index 0 as a BSP and treat the rest CPUs are APs. The BSP boot to the set code, and the APs are parked in a special location and wait to be woken up by the BSP. The initial state tells you where what is the virtual CPU index. In order to get the total vCPU number, use a TD core VPInfo. The number of vCPU is returned in R8 register. The TD core is a special core to the Intel TDX module. It can be initialized by the guest TD. The first TD VM core is to invoke the VMM services. We will discuss the detail in the next page. The TD call VP info is to get the TD information. For example, the GPW is returning RCX and the vCPU number is returning R8. TD call RTMR extend is to extend the TD runtime measurement register. The RTMR is similar to TPM PCR register. In current generation, TDX implement the RTMR with SHA-384. The TDVF will use this TD call to extend the firmware configuration and OS loader to support the trusted boot and the remote attestation. The TD call VE-info get is to get the virtual exception information. It will return the exit reason and the instruction information. TD call MR report is to return TD report. The TD report is a measurement of the TD and the TD configuration and Intel TDX module, etc. TD calls CPU VE set is to control the unconditional pound VE on a CPU ID instruction. Last but not least important is the TD call page accept. This is to accept a pending private page. TDVF will use this one to accept a page declared by VMM. TD-VM call is introduced to let TD invoke the VMM services. First, TD-VM call get TD-VM call info is to enumerate the VM call capabilities. TD-VM call map GPA is to request the VMM to map a guest physical address to a private page or a shared page. TD-VM call get code is to request a code enclave to sign the TD report to be a TD code. The TD code is for remote attestation. There are a set of instruction-related VM calls, such as CPU ID, halt, IO, read MSR, write MSR. They are to request the VMM emulate the instruction. Last, the pound VE request MMIO is to request VMM emulate the MMIO access. The memory management is one of the most complicated part of a TDVF because of the new concept. In a traditional VM, we only have the physical memory and MMIO. In a TD, there are three different types of physical memory: the private memory, shared memory, and unaccepted memory. The default physical memory type in a TD is a private memory. It means the TD memory is encrypted by with a TD specific key. The VMM and other TD cannot access it. There are two ways to create a private memory. The first is that VMM build a TD, and the VMM can use a SIM call page add to add a memory page for the TD. Then this memory is a private memory. The second way is that the VMM can use the SIM call page awk to declare a memory page for the TD. Then the TD need to use a TD call page accept to accept this one. Then this memory becomes a private page. The TD can access that private memory directly. Shared memory is a memory that can be accessed by the hypervisor. It can be used for hypervisor communication or virtual device DMA. The shared page setup is same as a private memory. The only difference is that there is a shared bit in the page table entry. It's also known as S bit. When the S bit is clear, accepted by the TD yet. The unaccepted memory is added by VMM by use the SIM call page awk. Then the TD must use TD call page accept to change the unaccepted memory to a. The unaccepted memory cannot be accessed before it is converted to a private memory. As such, there's no need to create a page table entry for the unaccepted memory. The last type is MMIO emulated by the VMM. The MMIO cannot be accessed by the TD directly like the physical memory. The TD must use a TD call VM call request MMIO to access the emulated MMIO. If the TD accesses MMIO directly, then the .v won't be triggered. Then the .v handler may use VM call to access MMIO and return the result. The memory type, because adding a TD private memory is time-consuming, the VMM may choose to add a small amount of private memory by default and declare the rest uninitialized memory to be unaccepted memory. Then the TDVF or OS may use TD call to accept the unaccepted memory to the private memory in lazy memory initialization. The private memory and shared memory transition is for communication buffer setup and teardown, especially for DMA access. To change a private memory to a shared memory, the TDVF need to set the S bit in the page entry, then use TDVM call map GPA. To change the shared memory to a private one, the TDVF need to clear the S bit, then use the same TDVM call map GPA. After that, the TDVF need to use TD core to accept this memory region again to be a private memory. The figure shows the memory state transition during boot. First, the VMM adopts the add the minimal private memory to a TD, include the TD hop, and the TD for stack and heap. Second, the TDVF may set up more private memory to continue running the whole system into a UEFI environment. Third, TDVF may choose to initialize all TD private memory. This step. Fourth, if a virtual device requires a DMA buffer, then the TDVF converts the private memory to shared memory. Fifth, after the DMA buffer is used, the TDVF converts the shared memory back to a private memory. The four memory types may exist in different phases. The private memory is the default memory type. There's no need to indicate that in UEFI memory map or PIGCD. The shared memory is same as the default private memory. There's no special indicator other than the page table S bit. The unaccepted memory is a special one. The TDVF need to report the unaccepted memory to OS because the TDVF might not convert all unaccepted memory to private. Then the OS may convert them later. A new UEFI memory type, unaccepted memory, is defined as indicator, similar one in GCD, PI hub, and ACPI E820. The MMIO does not need to be reported in a UEFI memory. The ACPI table in TDVF is similar to the one in OVMF. All CPUs are reported via MADT ACPI table. However, it's the mailbox structure and reports it to OS. At the same time, all APs loop to check the wake-up vector. After OS fills the AP wake-up vector, the APIC ID then update the wake-up command in the mailbox. Then each AP checks the command APIC ID and jump to the wake-up vector if the APIC ID matches. The TDX support the measurement and the remote attestation. Similar to TCG TPM-based static root of trust for measurement, the TDX boot flow extends the boot components into a set of measurement registers. The TPM defines the 8 PCR register for firmware boot. In TDX, there are two types of measurement register, one TDMR and 4 RTMR. First, when VMM constructs the TD, the VMM will use the SIM core and MR extend to measure the initial TD private memory to TDMR. Second, after TD launches, the TDVF may use TD core RTMR extend to measure the additional TD private memory in runtime measurement register. There are totally 4 RTMRs. This table is the comparison between the TCG measurement and TD measurement. So first, the firmware code goes to RTMR. It is done by VMM. The firmware data configuration goes to RTMR 0, such as the build time configuration firmware value. For example, if the ACPI table is from VMM, then the ACPI should be measured. The OVMF uses the firmware config IO selector and the firmware config IO data to get the configuration from QEMU. If so, all those data from QEMU should be extended to RTMR 0. The secure boot configuration is also a boot-related code and data goes to RTMR 1, such as the OS loader code and disk GPT partition. For the TDOS, TDOS kernel may extend the TD application to RTMR2. RTMR3 should be reserved for some special use only. Below this figure shows the TDVF measurement in a summary. The TD lightened VMM load the measurement TDVF to boot FV into the TDMR. Then the TDVF measures the config FV and the TD hop into RTMR 0. Then the TDVF measures the OS loader and the disk partition to RTMR 1. If a remote entity wants to test the report in RTDMR and 4 RTMR information. We have introduced a full TDVF, which provides the UEFI services to a TDOS. However, in virtualization environment, not all OS require the UEFI, such as a container use case. The container may just need a lightweight virtual firmware, such as a cloud hypervisor firmware. In order to support that case, we need a TD-shim concept. TD-shim is a tiny TDVF. It only includes the SEC initial program loader, IPL, and does not have any UEFI core. Instead of boot a UEFI core, the SEC IPL can boot to any payload, such as a UEFI payload, a container payload, or even Zephyr. A TD-shim does not include any device driver. It may use static ACPI table, or if that is true, the MADT wake-up structure can be used. If the TD-shim does not have ACPI table, it can use other table to report such information, such as MP table extension. Because the TD-shim does not produce UEFI memory MAC, you can just use E820 table to report the memory location, including the unaccepted memory. The trusted boot can still be supported. The TD-shim may extend the TD hop and report the event log in another static table. And this figure shows the TD-shim boot flow. The reset vector parks AP and switch to a long mode. And set up stack for C code and jump to the IPL. The IPL code measures the TD hub, pass the TD hub, get memory information, accept the private memory. Then it can load the payload and jump to the payload. And the payload could be UEFI payload, and it could be container payload, or even a Zephyr RTOS payload. We did the prototype. It shows a small reset vector could be 32K, including a fixed page table. A small IPL could be 25K byte, including a SHA-384 hash algorithm. In this talk, we described the Intel TDX. It supports the memory and CPU state confidentiality and integrity. It supports measurement and remote attestation. We also introduced the architecture of the TD virtual firmware, and the TD virtual firmware can build the chain of trust for the TD and launch the TD Enlightened operating system. Here is a reference for our talk. Intel published the TDX specification and the white papers on the UI, and for virtual firmware, we produced the Intel TDX virtual firmware design guide, and the guest hypervisor communication interface describes the interface between TD and the hypervisor. And we also open sourced the pre-production the TDVF code. It is on the EDK2 staging tree. My presentation, if there are any questions for this.